Let's try for an application of Gauss's law for a situation where we might first try to find the electric field from an object, but discover that the process is difficult, and it'll also be a check on our methodology here. So in this case, we want to consider a very, very long wire, an infinitely long wire of some charge, and we'll say it has charge density lambda. And we want to try to figure out what would be the electric flux we would measure at some point P here. Now, since the wire is infinitely long, then we're not really, considering how close we are from one edge to another. So we could basically, think about this being at like the midpoint of some very long wire. And we can draw the perpendicular vector here. And we want to try to figure out then what's going to be the electric field as measured at that point P. So we want to set up our coordinate system with x and y. And one of the things you're going to probably already expect is that the electric field in the x direction to be 0 at point P, because there's just as much charge to the left as there is to the right, so you'd expect that sort of cancellation. So there's only the electric force that's going up towards that point that we would be worrying about. So just from that sort of symmetry we see here, we can already exclude half the work. So that's a good start already. But now we need to try to figure out what might the electric flux be there. So we want to first, look at some infinitesimal region and figure out what's supposed to be the flux from, or I should say the field from that little amount. So if we have a little dx, and so it's going to be distance x away from our origin point. We're going to be distance a away, we'll say, from the wire itself. And we can, of course, draw a vector here, call that distance r. There's an angular system we have here, just for completeness. So that's our basic setup then. We have already defined what our infinitesimal region is supposed to be. And now if we set up our integral very carefully, we should be able to find what is the electric field from this. So we'll put this up into the corner for now and start trying to set things up. Now, an infinitesimal amount of charge will give some sort of infinitesimal electric field that we're going to talk about. And remember that it was defined as 1 over 4 pi epsilon naught, little infinitesimal charge divided by r squared. Now, we have again a way of relating that infinitesimal dq charge to something else we can integrate over. That dq is going to be simply lambda, the charge density of this wire, dx. Okay? Now, another thing to consider is the fact that r, that distance away from point P, is going to have an x dependence. We can see quite simply from Pythagorean theorem that r squared is supposed to equal a squared plus x squared. That much seems to be fairly true. But we could also rewrite this in a different way if we wanted to put the angle in there. So I'm going to do that for now just as a choice. It ultimately doesn't matter, but you'll see what I'm going to try to do with that fairly soon. So in that case, we see that cosine of theta is going to equal the distance we are from wire A divided by r. Or simply then we could have r equals A divided by cosine theta. All right. So we can go ahead and plug that much in right now and see how far it gets us. And so we see the infinitesimal electric field, 1 over 4 pi epsilon naught, lambda dx, and then we're going to have a squared cosine squared theta. So far so good. But remember, there's something else we need to be considering here. We need to be considering the amount of electric field in the y direction. So what I wrote at the top here is actually a bit incomplete. We have to talk about how much E field is going up in that direction, and that's going to depend then on the angle we have. If the infinitesimal charge were right beneath P, then the electric field line would just go straight up through P. But instead, we're off at a bit of an angle, so actually we need to include also a bit more to this. We're going to have to include cosine theta here. That's the component of the electric field from that little infinitesimal charge going up through that. So multiply with that, and it means we also have to include that down here, times cosine theta. Okay, now, so we have dx. We could try integrating over that, but we see that the angle is going to have some sort of very direct relationship with x. So let's try doing that and see what else that's going to give us. We'll make a little bit of space again and get set up another relationship that we see that actually tangent of theta is going to equal distance x over distance a, just from basic trigonometry. Or in that case, then we'd see that x is equal to a tan of theta. All right. And the reason we've looked at this right now is that if we wanted to look at an infinitesimal x region, we take the derivative of the left side, that would just be dx, that'd be the infinitesimal. And on the right side, we would have a, if you remember what your derivatives then of tangent are, we're going to get secant squared theta d theta. Now we can see we have a nice simple relationship, or maybe not so simple, relationship between infinitesimal x region and an infinitesimal amount of angle. So we can actually plug that into our handy-dandy equation. So let's bring that all down and put it all together and see that electric field in the y direction is going to be lambda 4 pi epsilon naught. We're going to have secant squared theta cosine cubed theta. Don't forget the a, the distance a, when we went from dx to plugging that in to get to our little infinitesimal region. This is still also divided by the original a squared we had from before. So this right here is now down here. We didn't forget that, fortunately. And then also multiply by infinitesimal that. All right. Now you might think that looks absolutely freakishly awful to integrate. But remember that secant of theta is equal to just 1 over cosine of theta. Well, you see that just simplifies wonderfully. So let's move this then out of the way and do some of our final steps. We'll take integrals of both sides, because we love doing our integrals. And with that, we see the electric field in the y direction is going to equal lambda over 4 pi epsilon naught, 1 over a, and we're going to take the integral of cosine, no square, just regular cosine theta, d theta. Now, what are going to be the integration limits here? We haven't talked about that so far. Well, if we have a wire that is infinitely long, that basically means that that angle that we drew here originally is going to become as large as it possibly can as x moves along that way. And if x is infinitely far away, then actually that angle is going to become 90 degrees, or pi over 2 radians. And that's going to be the same going from the right as well as to the left. So our integration limits are actually from negative pi over 2 to pi over 2. So if we take that integral, we plug in our limits, we are going to find then that the strength of this, we found that, for example, we're going to find that this integral is going to give us a nice value of just 2. Nice and simple considering all that. So the electric field is also going to be lambda over 2 pi epsilon naught a. Again, this is for a very long or infinitely long wire. Now, as you saw, that was a lot of work. There was a lot of caution we had to take, a lot of substitutions, and with vector stuff as well, a lot of opportunity to make mistakes. So let's now try this with a different methodology, trying to use Gauss's law. So the same sort of setup. We have this infinitely long wire of charge density lambda, and we want to find the electric field strength at some point P, which is going to be, in this case again, we said distance A away. But before I draw anything like that, what we want to do, if we want to use Gauss's law, is to set up some sort of Gaussian surface. So we want to consider the symmetry here, and what sorts of simple shapes that could we have that would enclose this sort of thing that we could play with. Now, spherical symmetry isn't going to work so well, because you can imagine that while the electric field lines are going to be coming straight off of this wire, all those field lines are going to be pointing up straight in both directions. So if you had a sphere encompassing this whole thing, sometimes those lines would be perpendicular and sometimes not. So that actually isn't going to be the most secure route for us, unfortunately. We need something that can basically go, stretch along the wire we have here, and still, of course, has some sort of simple shape for us. And in this case, I am going to choose my integral surface to be a cylinder. So this cylinder, we can say it has a radius of A, and it has length L. And right now, actually, L is going to be what I'm going to call a dummy variable. You're going to see that no matter what value of L I plug in, it's not going to matter, but we can just start off with at this length, and we can then imagine the cylinder stretching to whatever length we want. But this will be our first basic point of setup. Now, why did we do this? Well, what is the surface area of a cylinder? Well, remember that a cylinder is basically two circles and then a surface connecting the two if we stretched it along. If we took a circle and just stretched it along that length. So we know what the surface area of, we know what the circumference of a circle is. Circumference of a circle is just 2 pi r. So if we take that circumference and just stretched it along the whole way, we know that the area is actually going to be 2 pi r length of that cylinder. In this case, our radius is actually, I'm calling it A, so let me put the proper variables in as I wrote them. So, why does that matter to us? Well, now again, we have actually everywhere the field lines are going to be going up, it's going to be hitting that surface perpendicularly. And again, I know that due to our symmetry here. Our wire being long, all the field lines are going straight up, and so everywhere that cylinder is, it's going to have its surface perpendicular to any of those field lines. So if we then start setting up our flux equation for Gauss's law, because we're enclosing a surface here, remember that is equal to the surface integral of E dot dA. And we've set up everything to be perpendicular, so we're going to just have surface integral E dA. And since our E field does not actually have any dependence on the area, it's actually a constant in this case, so actually we can just take it out of the integration at all. So it's just E integral over dA, and that's just going to be EA. So far, so good. Okay? And we remember from Gauss's law that the relationship then with the flux we have here, that is simply going to mean this whole thing has to equal the enclosed charge divided by epsilon naught. Now, how much charge do we have inside? Well, that's going to depend on basically how dense the charge density is and how long a length we're enclosing, which in that case will be length L. So we know what the enclosed charge is for our Gaussian surface that we've imagined drawing over this thing. So we can actually start then plugging things in. we give ourselves a little bit of space to work with, we're going to now attempt to rearrange a few things. So again, we know what the surface area is. So if we take EA is supposed to equal lambda L divided by epsilon naught, in that case the electric field is going to simply equal lambda over L over epsilon naught divided by 2 pi A L. And you can see that simplifies to lambda over 2 pi epsilon naught A. Look familiar? It's the exact same result that we had from before when we had to do that much more difficult integral. So you see that this is the sort of power that Gauss's law has. If you choose a Gaussian surface with a symmetry that matches what you're trying to hook up to, you're going to find that actually it is a whole lot easier to do these sorts of integrals. Now, if I did this with a sphere, I'd have to worry about the vectors not being perpendicular, and then when I did that surface integral, it would be a lot more complicated. Fortunately, I avoided that by choosing a surface that would be nice and symmetric about our object. So this is going to be basically the more challenging point, is choosing the Gaussian surface, but if you choose correctly, you see that the process is immensely simple, and you're going to get the answer you want that otherwise would have been much more challenging to achieve.